Okay, I think we're ready to get started. Well, welcome everyone to today's technical webinar from Freedom. My name is Ken Delaney, and I'm the Director of Industry and Innovation. We are a Power Systems and Power Electronics Research Center at NC State University. Our research projects span renewable energy integration, electric vehicle technologies, control techniques, microgrids, applications of wide bandgap semiconductors, and traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for hardware in the loop development, an electronics packaging lab, and a high bay lab for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners like ABB, Duke Energy, and the New York Power Authority, we are leading the electrification revolution. Hopefully, everyone is familiar with Zoom. We have disabled audio and video for all participants, and we ask that you use the chat feature to ask questions. Just hover your mouse over the Zoom window and the button should appear at the bottom of that window. Click chat, type your question, and we'll answer as many as we can. Note that this webinar is being recorded and will eventually be posted to the YouTube channel for the Department of Electrical and Computer Engineering at NC State. So now, I'd like to turn things over to our presenter.
Hello. Hi, everyone. Thanks for attending this webinar. I'm Nilüfer Gambari, a PhD candidate at NC State University Freedom Systems Center, and I'm going to present one of my recent work that we have done recently. And listening to this presentation, and I'm looking forward to your comments and questions. So the presentation topic is the frequency decoupled energy management system for storage units in DC microgrids. And I'm going to explain what it is. First, let me jump into the introduction. And I'm going to bring up the concept and the idea of microgrid, what it is, and why we are leaning toward microgrids. As we all know, microgrid is the concept of renewable resources energy storage systems integration into a controllable grid. Microgrids can operate in the islanded mode or grid connected modes, depending if they are connected to the grid or if they are far from the utility grid. They can have different applications, and here we are categorizing them into different ones, like the all-electric shipboard, the more electric aircraft, and let me drag it here. Okay, and the more electric aircraft, and it can be a building scale application. It can be any different application, and in most of them, we have energy storage systems that are abbreviated as ESS. They are operating in an islanded mode with DC voltage. So DC microgrids would offer direct connection of the generation side to the consumption side with lower conversion stages. What does it mean? This means that when we have different sources, different generation sources, that they are producing DC power, like renewable resources like PV arrays, wind turbines, or any kind of energy storage systems, it is better to utilize DC microgrids to take advantage of all the benefits, because DC microgrids can have a direct connection of the generation side, which is DC power, to the DC loads directly, and the conversion stages would be much lower. In all DC microgrids, we would have a decentralized and flexible control platform, and that, we would have a decentralized and flexible control platform. And in this control platform, we are managing the power flow among different kinds of sources. So when we have different applications of DC microgrids, and especially the application of more electric aircraft, we would have different kinds of energy storage systems in the microgrid. The design of these ESS is a key role in microgrids in MEA applications to make them optimally operate and protect the electrical generator. Why the electrical generator? Because this electrical generator, or it could be the utility grid, they would have slower dynamics and they are very sensitive to the variations and deviations in the production or in the load. So the ultimate goal is to have and protect the electrical generator such that they operate optimally, and we are going to protect them from producing any deviations and variations in the load side. We have itemized and categorized different ESS technologies into 3 different categories. They could be in the category of lithium-ion batteries, in the fuel cell, or in the supercapacitors. But how these are categorized? We are putting each ESS in each category according to the response time, to the capacity, to the power and cost, and to overall dynamic of the system. So if a battery has a slow dynamics, it would fall into the fuel cell. And if it has a medium power density and medium dynamics, it would fall into lithium-ion batteries. And finally, supercapacitors would have a very fast dynamics. In all these microgrids, in order to satisfy all demanded energies with different requirements, we need to implement different ESS in the system. So all these different kinds of ESS should be implemented in the DC microgrid to make them satisfy the demanded energy. Let me explain what is the studied DC microgrid that we have here. Take a look at this picture. It shows a schematic of the studied DC microgrid. We have the DC bus and all sources and loads are hanging from it. You can see that we are categorizing the energy source systems into 3 items. We would have fuel cells, we would have batteries, and we would have supercapacitors. They all produce DC power and they are connected to the DC bus through DC-DC buck converters. Here you can see that these converters are considered bidirectional because batteries and all energy source systems can operate both in the charging mode and discharging mode. And so they can produce power or absorb the excess power. So these DC-DC converters should operate in the bidirectional mode. Then we would have the electrical generator or the utility grid in different applications that they are producing AC power and they are connected to the DC bus through AC-DC rectifiers. And here you can see, according to this power flow arrow, that the direction of power flow is just unidirectional. This means that the electrical generator cannot absorb the excess power and it can only supply the required power. Here you can see that we have different kinds of loads. They are all parallel to each other and they are aggregated into one load that is connected also through a DC-DC converter to a DC bus. And here, according to the direction of arrow, you can see that the loads are only absorbing the power. So here, through this figure, we can show what the benefit of DC microgrid is. Here you can see that the different kinds of sources, they are connected to the loads directly only by means of DC-DC converters. And no AC-DC rectifiers are added to the system. And this would result to a high power density and lower cost of the system and higher efficiency. So this is the main concept and idea that we are using DC microgrids for further studies in different applications. Let me explain the concept of EMS, the energy management system. We would have different kinds of sources and generation resources in the system. We would have electrical generators or the utility grid, and they would have slower dynamics with respect to other ESS of the system. Also, we know that if we have renewable resources like wind turbines or PV arrays, they would introduce intermittency to the system. On the other hand, we have loads that these loads would have variations in their natures, and these are things that they cannot be expected, they cannot be estimated, and they cannot be predicted. And these variations, either in the load side or either in the renewable resources, are detrimental to the operation of the electrical generator. So this is why we want to protect the electrical generator from providing any of these variations. The ESS should provide an uninterruptible power supply, and they are considered as a compensation for the electrical generators. And also we know that the variations in the demanded loads or the renewable resources, they would introduce high frequency transients. These high frequency transients can last minutes or seconds. The ultimate goal is to protect the electrical generator to provide these kinds of variations. But how we are going to do this? This is the concept of energy management system and EMS, that we are categorizing sources into 3 different items. We know that quick load variations would affect a fuel cell's life. So fuel cells are seen as of electrical generator be protected from providing the variations. Also, lithium-ion batteries, if they provide fast changing recurrence, very fast and burst power, they would be exposed to temperature increase and decreasing in efficiency and lifetime. So they should also be avoided from providing very fast changing currents. On the other hand, supercapacitors, compared to the battery and the FC, they would have medium power density and they can supply surge power without influence on their lifetimes. So this is where these supercapacitors are taken into consideration, because this ability of the supercapacitor makes them capable of providing fast transient loads. So we are consider supercapacitors as the primary source of providing surge and burst power in a microgrid where we have different kinds of sensitive and slow dynamics resources.
Hey, Nilüfer, we do have a few questions in the chat, and I just want to ask you those briefly. One attendee noted that fuel cells may not work in both directions. And I know that you can design fuel cells so that they can be both, generation and storage, which I think is what your analysis assumes.
Yes, fuel cells mainly work just in the unidirectional operation, and this is another point of view that they can be seen as the like the electrical generator in the system. But the other energy sources of the system, like battery and the supercapacitor, they can operate in the both directions.
And then there's, in your earlier diagram, it seems to indicate that the loads are only DC loads.
Yes, actually they can be all DC and AC loads in the system. Let me have that diagram again. Okay, here, yes, you're right. I have only DC loads in the system. They can be AC and DC loads in the system, but what we are focusing now, we are focusing on just the generation side of the system. And that's why we are considering just DC loads for the simplicity. But they can be any different kinds of loads to the system, but they would be connected to the DC bus through AC-DC rectifiers. But we are just focusing on this part of the system, and we are focusing on the energy management systems.
Great. And then, yeah, one person has asked if we're going to talk about protection aspects in DC microgrids. And again, that's not the focus of your presentation today, but I know that's an important topic.
Yes, protection is another topic, which is a very vast topic, and it needs a very different literature and very different algorithms. We are here trying to protect sources from producing any variations. We are not thinking about faults in the system, and the objective is not protecting the sources from providing the fault currents, but we are just trying to smooth, make the power to be smooth regarding different energy source system point of view.
Great, thank you.
Mm-hmm. Thanks, Ken. Thank you, Ken, for asking the questions, because I don't have the chat box open because I'm in the presentation mode and I cannot take a look at them. Just please let me know when we have questions in the chat box. Okay, I was in this slide, and let me explain the idea how we are gonna protect different kinds of sources in the system. Here, it shows the load current that has variations, and it's kind of a random load power that we have during different times of operations. What we want to have is fuel cell or the electrical generator to provide as a smooth power as possible. So we are assigning the offset of this curve to the fuel cell, and we want to have the supercapacitor to provide the fast changing portion of this load power. So these type of summits and alleys of this curve would be assigned to supercapacitors. And then we would have a battery power to produce the remaining power. So the remaining power would be assigned to the lithium-ion battery. So this is how we are assigning different portions of the load power to different energy storage systems. We would have a decentralized control platform in a DC microgrid, and each generation source would have its own controller. And the main idea of having the controller is the droop control algorithm. This is a decentralized method in which we are controlling each source of the system. We are trying to have a frequency decoupled algorithm to protect the sensitive sources like the electrical generators from supplying burst power. So we are trying to look at the load variations from the frequency point of view. If we protect the electrical generators, and they're going to be protected from any variations in the system. And this is where the concept of frequency decoupled energy management system is going to be taken care of, where we require the energy to be decoupled in the frequency point of view. In most of the recent studies and in most of the literature items, we found that the dynamic performance of the ESS was neglected, and the characteristics of the energy source systems have been overlooked in most of the recent studies. So the main contribution to this work is to propose a droop-based control algorithm that can decouple the current into different components, and then we want to assign them to different energy source systems. So for any kind of energy source system, we would propose a new different droop-based control algorithm that can compensate the power from the frequency point of view. Also, we are trying to address the plug and play feature by introducing this adaptive droop controller that they can be assigned to any number of ESS in the system. So another good contribution that we have here is that we are not introduce any limitation to the number of ESS in the system, as some of the recent literature did. Also, this EMS is required to prioritize the ESS according to their characteristics. So we are prioritizing different energy source systems, and I'm going to explain later how. The objective is to keep the FC power constant, or it could be the electrical generator, or it could be the utility grid. Any slow dynamic source, it is needed to keep their power to be as constant as possible, while the supercapacitor would compensate for the fast changing fluctuations. Also, we would have batteries that they would provide power with lower fluctuations. Let me explain the concept of droop controller here. As you may know, we have conventional droop controllers as series in the sources. So when we have a converter operating in the droop control algorithm, it can be seen like an ideal voltage source in series with a virtual resistor. However, here we are trying to change the virtual resistor to a transfer function that we can decouple the load current between two or more different energy storage systems according to this proposed transfer function. So here you can see that we have the formula of droop equation such that the output of each converter is defined according to the nominal voltage set point to the proposed transfer function and output current of the converter. The transfer function that was defined in the previous section was explained in the previous section. It is defined here like a first order low pass filter that it is in the Z domain, something like this. We are transferring it from Z domain to S domain such that we are controlling the system in a low pass filter mode. Here you can see that the Z domain and the S domains can be transferred and can be calculated from each other just by knowing the time step of the system. And we are defining the system first in the S domain and doing all the calculations. And for the real-time implementations, we need to move back to the Z domain to implement them on the digital controllers. I'm going to explain later how in the real time the digital controllers are taken into consideration. But here, this alpha is the filter parameter that they would define the cutoff frequency. So by playing with this alpha, this parameter, we can have different kinds of filters in the system, and we are assigning each of them to each ESS of the system that corresponding to the specific component of the load current. Let me show the body plot of the filters of the system. Here, as you know that the load current is going to be decoupled into the first and second converter according to the droop equations. So here we change the droop resistive to be a transfer function. So the load current is going to be decoupled to I1 and I2 according to G1 and G2, which is derived from the droop parameter transfer functions. So here, I'm going to show you the body plot of the G1 and G2. The blue curve shows G1 and the red curve shows G2. Here you can see that G1 would pass almost all low frequency, very low frequency components of the load current, and then it would assign these low frequencies to the first converter. However, we would have G2 and it would pass all the high frequency components, and it would assign the other converter all the high frequency components of the load current. So here you can see that this is the cutoff frequency, and by playing with the alpha and the parameter of the filters, we can have different cutoff frequencies for different filters of the system and how we are decoupling the load current into different components. So let's consider here we are having 3 ESS in the system. So we would have 3 different filters and transfer functions in the system. They are all first order low pass filters, but they would have different alpha, different parameters of this filter. And here we are assigning one of them to have a very low amount of alpha. So we are assigning F1 to the FC due to its lower filter parameter, so that the FC would be responsible for very low frequencies. Then we would have a F3 that it has the highest amount of the filter parameter. So we are assigning it to supercapacitor for passing the high frequency components due to its higher filter parameter. Then we would have something in the middle. The filter parameter would be in the middle of these two, and we are assigning this filter transfer function to the battery for making it responsible for the remaining power. The body plots of these transfer functions are shown here. You can see that F1 that has the lowest filter parameters, it has the lowest cutoff frequency as well. And here you can see that by playing with the parameter alpha, we are changing the cutoff frequency of the filters. So the first filter that has the lowest cutoff frequency is assigned to FC, and it would make the system make that FC to produce the low components of the load power. Then F3 is going to be assigned to the supercapacitors, and it would frequencies to the supercapacitors, and then the middle frequencies is going to be assigned to the battery.
So Nilüfer, back to that slide, there's a question, how do you come up with the exact values of alpha for the transfer functions?
It is an iteration thing that we just select a random number and we see how the system is going to respond back. And also through the mathematical equations that I'm going to explain in the next slide, we decide how these numbers of the alpha should be to have a stable system.
Okay, so there's a stability component, but then it's also hardware dependent, right? I mean, so
yes,
I know that for each different energy storage system, you pick one, but if you had, you know, fuel cell model A and fuel cell model B, they might have different parameters.
Yes, they would definitely have different parameters if they would have dynamics, and these parameters are going to selected according to the stability of the system. So we are taking care of the stability point of view, and we are going to have the mathematical model to define these parameters. I'm going to explain them in the next slide.
Good, thank you.
Here is the block diagram of the controllers and the hierarchical platform. We have the bidirectional buck converter here, and then we would have a current controller and a voltage controller as the inner control loops. They are here for ensuring the stability of the system. And here you can see that they are considered as PI controllers. And deriving the mathematical model of the system from the looking through the state space model. So we are defining different state variables of the system. For each of the current controller and voltage controller, we are going to have two different state variables of the system. And then we would have droop controller. In the conventional droop controller, it is just a virtual resistor value. But here in the proposed method, we change this one to be a transfer function. And so this transfer function is going to introduce another state variable to the system. So we are looking through the quantitative examinations, and this is needed for each ESS in the system and the associated controllers. So we are creating the mathematical model using the status model. I have skipped all the equations here because it would be a very long and huge equations, and I have the conclusions here that we have derived this mathematical model. This is status model that you can.
Hey, Nilüfer, your audio has gone out briefly.
Let me stop my video and maybe it would be better.
Okay, we can hear you now.
Okay.
Yeah, so just restart on this slide. Thanks.
Okay. We're gonna take a look at the ESS and the associated controllers from the quantitative examinations. And so having the mathematical model to create this mathematical model and taking a look at the system from the frequency and mathematical point of view. So we are looking through the state space model of the system. I have skipped having the equations all here because they would be very long and huge equations. And I would have here only the state space model. Here you can see that we have 5 different variables of the system. And here you can see that this A matrix of this state space model is related to different parameters of the current controller and voltage controllers, as well as the output filters of the converter. So for each ESS and each converter of the system, we need to have this kind of state space model to define the stability of the whole system. Here also you can see that the load is gonna aggregated into this item here in this index. And here you can see that also we would have all the filter parameters as N1 and D1 and N2 and D2 as different filter parameters transfer function. So we would have them like these variables in this system. And then through the stability, we are defining how this N1 and D1 and D2 should be. It seems that we have questions. Let me see. Actually, the current and voltage controllers are PI controllers. And if we write the mathematical calculation, they are be a fractional order controllers because they are considered a PI controller, and they can be also seen as like the first order filter from the mathematical point of view. So right, the current and voltage controllers are also fractional order controllers. And then another question we have from Anil. The system is explained in the previous slides. So we would have a DC microgrid, and for each ESS of the system, each generation source, it could be the fuel cell, it could be the voltage sources, or it could be the batteries. We would have a bidirectional buck converter, and we are creating the state space model for that system. And then we are combining that state space model for all the voltage sources of the system. Okay, thanks, Ken, for answering to that question. And then I would have another one. Is there any assumption? Okay, these states are defined here in the previous slides. Yeah, the assumptions are first taking into consideration that having the, for example, ignoring the line resistances in the system and these kinds of assumptions, and we are defining the state variables according to this block diagram. We would have the first state variable as the output current of the converter. The second one is the output voltage of the converter. The third one is the voltage controller relates to the voltage controller. And the fourth one is related to the current controller. And then the last state variable is related to the transfer function we're proposing here. Another question as well. Okay, once we derive the state space matrix and model, we are looking through the eigenvalue matrix A, and by observing them, we are questioning and assessing the system stability for different filter parameters. So here we are seeing how these filter parameters can be selected such that all the eigenvalues of the system for different loading options are going to be all negative. So here it is shown that if we change the load resistive value for different amounts and change the filter parameters, we would have the stable system. And so these range of filter parameters would let us select them such that the system is going to be stable. Let me explain the ideas of EMS and frequency decoupling in the simulation results. The objective is to having the electrical generator or FC to produce power as smooth as possible, while other ESS would compensate for the load power variations. So we would have two case studies here. In the first one, we have lots of variations in the generation side. So we have PV arrays in the system, and these PV arrays are considered to produce lots of variations according to the different times of the simulation. Here you can see that these variations are coming from different in the nature of the PV arrays. They cannot be estimated, they cannot be predicted. One thing that we can do is to decouple them into the frequency point of view such that to protect the electrical generator from producing such variations. And here you can see that the electrical generator producing the smooth power like this purple curve. However, the supercapacitor is responsible for producing such burst powers, and you can see that these fast changing powers are going to be supplied through the supercapacitor. And then the battery would produce the power in the middle. So you can see that the power of the battery is not as smooth as the electrical generator, and also it is not as burst as the supercapacitor. So the objective is achieved here through the frequency decoupled algorithm. Let's see how we can have this, the concept of this into having different load type variations. So in the previous case study, we have the variations in the generation side, but here we have the variations in the load side. So we are applying the same
Hey, Nilu, we lost audio again.
Sorry for that. Here we have a different. Can you hear me now?
Yes, we can.
Okay, sorry for that. We have different variations in the load power here, and the same kind of random variations are applied to the load power. And we would have three different ESS, FC, the battery, and the supercapacitor. It is desired to have the FC to fuel cell to produce as a smooth power as possible. And here you can see that fuel cell has the power as smooth as possible, and it is always positive. So it's that in the unidirectional mode. And then we would have the supercapacitor to provide the surge and burst amounts of the power. So here you can see that how fast changing the power of the supercapacitor is. And then we would have the battery to produce something in the middle. It is not as smooth as the fuel cell, and also it is not as fast changing as the supercapacitor. So the objective here is also satisfied, and we can simply decouple the power fluctuations into different portions, and we are assigning them to each ESS of the system. Then we have applied the idea and the control algorithm onto the hardware in the loop setup. So this is the hardware in the loop setup shown here. We have the Typhoon hardware in the loop system here. This is Typhoon 602, which is the newest version of Typhoon that we have in the lab. This hardware in the loop device is responsible for simulating all the bulky items of the system. So the PV arrays, all the energy storage systems, the electrical generator, and all buck converters are modeled inside the Typhoon software. Then we are going to implementing the control ideas in the digital controllers, like the Texas Instrument DSP boards. They are used for implementing the control methods. And then they are communicating with the HIL setup through the microgrid interface board. They are sending the gating signals of the converters, and they are measuring the analog and analog inputs of the outputs of the system. So by having this communication among the digital controllers and the system, we are going to implement the idea, and the results are going to be shown from the Typhoon point of view. The case study here is a DC microgrid with a constant load of 3 kilowatt. That it has variations in the generation side. So we consider that we have a PV array current of 70 ampere for 2 seconds, and another constant current of 80 ampere for 2 seconds. And this cycle is going to be established for the whole duration of the real-time simulation. So as you see that these PV arrays have variations, and it's not smooth fun, and it is a desire to have the variations to be decoupled into different portions, and they are going to be assigned to different ESS of the system. Okay, here the simulation results are shown here. So you can see that we are assigning the smoothest power to the FC. So here you can see that the FC, regardless of their own ripples that is derived from their output filter of the converters, we are not dealing with them now, but you can see that the overall power of the SC is smooth. However, the supercapacitor current has lots of variations, and it would produce fast changing power and current. And also the battery would produce something in the middle. So you can see that the variations in the generation side is decoupled into different components. So let me jump into the conclusion. We had a DC microgrid with different kinds of ESS in the system. We were proposing an adaptive group control method to decouple any variation in the generation or loads. And the method splits the demanded current into low and high frequency components. And then we are assigning each component of the required power to different ESS according to their intrinsic characteristics, according to their dynamics. So the proposed method addresses also redundancy by providing the ability to assign the controllers to any sources of the system. So let's consider that we have more than 3 sources in the system or any different kinds of sources. We are first defining their dynamics. So for example, we have the slow dynamics, we have middle dynamics, and we have fast changing dynamics. And then according to their dynamics, we are defining the filter parameters and assign them to each ESS. Thanks all for listening to my presentation. I am ready for your questions and your comments.
Thanks, Nilfar. We do have a couple of questions from the chat. I think on slide 20, you have the plot showing maybe 19, maybe 21. There's some question in general about the percent contribution between fuel cell and supercapacitor. And just, you know, it appears that there's greater ripple in the fuel cell when there should be more ripple in the supercapacitor.
Yes, the concept is shown here. You can see we cannot define a percentage of the load. For example, let's say 50% is going to be supplied by the fuel cell and 50% is going to be supplied by the supercapacitor. There is not something like this, but we are trying to pass the smooth power of the load to the fuel cell and the surging to the supercapacitor. So let's consider that we have a very smooth load power. So all of them, all this portion are going to be supplied through the fuel cell because there's no variations, there's no deviations, and there's no fluctuations. But once the fluctuations are taken into consideration, this is where we need to have the supercapacitor to produce this surge of power and that fluctuations.
Okay. And I think there was another question about mimicking the load dynamics and choosing small signal stability. I may need to go back up a little bit.
Yes, I read it.
Okay.
I showed the equations there. Let me show them again here. You can see here through the smallest signal and through the state space model, we would have different filter parameters, and we are defining them all in the state space model. So we are mimicking the simulation and the actual converter in the mathematical point of view. And through the transfer function, we are decoupling the load into different components. And this is how we are trying to mimic the actual system in the state space model. I hope that I can answer that question. And let me see. I don't know why the chat box is not gonna be open for me. Okay. Okay, the next one is that okay, yes, it is recommended that supercapacitor is just producing only the fluctuations and not the smooth power. Yes, you're right. We can change the filter parameters such that the supercapacitor is only responsible for the high frequency components, and all the low frequencies is going to be supplied by the fuel cell. Yes, we have addressed this problem in the later work, and we are going to work on it by adding another portion to the transfer function to make the supercapacitor only supplying the high frequency components. So let me explain it. We have this kind of the transfer function here. We are playing with the denominator here such that making the supercapacitor to provide only the high frequencies and the steady state amount of the supercapacitor to be 0. So we are working on it. And then if you mean the hardware in the loop, yes, the ripples are going to come from the output inductor of the system. Here, they're going to come from the output inductor of the system, and we are not dealing with it right now. Just let's consider the average and the offset of each curve. And you can see that they have fewer ripples with respect to the supercapacitor, that the overall curve is going up and down, but this fuel cell curve is smooth. But just please ignore this ripples because they are coming from the output of the converters, and we are not dealing with it. We don't have control over that. But in the future, we are going to change the converter settings such that these ripples are going to be reduced.
And Nilu, I think it'd be good if you repeated the question before you answer. But I'll read
sure.
One of the last ones here is, are you considering the state of charge of the battery and the supercapacitor when controlling them in the HIL simulations?
The state of charges are not going to consider here. We are just taking a look at the dynamics and the frequency point of view. Actually, the audience are gonna share all my ideas that I would have for the future work. Right now, I'm working on combination of the state of charge of batteries into the frequency decoupling components and algorithms, and I'm gonna combine them together such that we have control over the state of charge of batteries as well. Suhanya asked about the elaboration on the electrical generator case. Actually, I have shown here in the simulation results that we have the electrical here, and we wanted to have the smooth power. Actually, the fuel cell and the electrical generators are all seen the same from the DC bus point of view. They have slow dynamics, and so we are going to see them the same. So here, in the first case study, we have electrical generator, but in the second case study, we have fuel cell. But they are going to both produce as smooth power as possible.
And Nilüfer, I think the question may have been more about specifics of the generator, like, you know, what's the assumptions on the, is it a turbine or the size of the diesel engine? And I mean, I know for your analysis, it's much more of just a generic generator.
Exactly, it's just a general case of the electrical generator. For the more electric aircraft, it could be a mechanical, like the motor, it can be a diesel generator, but we are not dealing with that. It could be any type, the electrical generator, and we are going to protect it from any fluctuations. And that's why we are not dealing with the generator at all. We are just dealing from the energy management system point of view. So we consider that we have a generator. It could be the utility grid. It could be the electrical generator in an islanded microgrid. It could be anything that it has this slow dynamics. So we are not dealing with the what drives the generator and what is the type of the generator itself. We are just dealing with the energy management side point of the view.
Right. Again, this is not a full microgrid simulator.
Yes, actually, we are just taking a look at the different energy source system.
Right. Well, so the last question I think we'll ask is, do you consider load side converter in the dynamic modeling?
Okay, no, we just consider loads to be a pure resistive DC loads, because as I mentioned earlier, we are focusing on the energy management system, and we can simply add other loads to the system. We can have CPL, we can have constant power load, constant impedance load, we can have AC loads, but they can be all also aggregated into a simple load, and we are dealing with the generation side. So that's the reason that we just consider only pure resistive loads.
Okay, great. Yeah, so thank you everyone for the great interaction through the chat, and thank you very much, Nilüfer, for your presentation, and congratulations on becoming a PhD candidate. That's wonderful. So Terry has reminded us to check the NC State Electrical Computer Engineering YouTube page in a few days, and we should have this posted. If you still had any questions or wanted to come back or share it with others in your organization. Thanks everyone for joining, and this concludes our webinar.